Hello to all of you. In the previous lecture, we have discussed about the solid state substances, in which the solid state substance we have considered the insulator, conductor and semiconductor. We have also gone through the properties of each one of them. We have discussed in the conductor that at absolute zero temperature also there will be some charge carriers in the conduction band, because of which the current will flow through the conductor. The conductor has a property that on increasing temperature its conductivity decreases, because on increasing temperature charge carriers of a conductor will vibrate and it does not allow the current to flow through it. So as the conductivity increases means it has a high resistance. So on increasing conductivity the resistance of a substance is increasing. This is known as the positive temperature coefficient factor. Means the conductor is having a positive temperature coefficient. We have also considered the semiconductors. In the semiconductors, we have seen that on absolute zero temperature, all the carriers will lie in the valence band and the conduction band will be remain empty. So we can say that at absolute zero temperature, semiconductor will act as an insulator. We have also seen the energy gap of a semiconductor, that it is 1.1 electron volt for silicon and zero point 0.7 electron volt for germanium. We have also seen that conductivity of a conductor lies between 10 to the power minus 8 to 10 to the power 37 per centimeter. I have also told you about the another semiconductor substance instead of silicon and germanium, that is gallium arsenide. Gallium arsenide has an energy gap value of 1.4 electron volt. It has the largest energy gap value, that is 1.4 electron volt. Germanium has the least energy gap value, which is 0.7 electron volt. On increasing temperature, semiconductor has a property that on increasing temperature the conductivity of a semiconductor increases, because when we increase temperature the electrons in the valence band acquire that much amount of energy. So acquires the sufficient amount of energy and they travel through the conduction band, and then the semiconductor conducts and it allows the current to flow through it. So we can say that on increasing temperature the conductivity of a semiconductor is increasing, means its resistance is decreasing. So it has a negative temperature coefficient. So we can say that semiconductor has a negative temperature coefficient factor. uh, we have discussed the three solid state substances. Now we see the types of a semiconductor. We have two types of semiconductor. First is the intrinsic semiconductor and second is the extrinsic semiconductor. Intrinsic semiconductors are those semiconductors in which the number of holes is equals to number of electrons, means they are the purest form of semiconductor. We have added 0% impurity in them. So intrinsic semiconductors are those semiconductors in which the number of electrons is equals to number of holes. Secondly is the extrinsic semiconductors. Extrinsic semiconductors are those conductors in which we have added the impurities, in which we have applied the doping process. So that type of semiconductor is known as extrinsic semiconductor, in which the number of electron is not equals to the number of holes. So these are the two types of semiconductors in which we are going to be which we will discuss now. Firstly, we will discuss the intrinsic semiconductors. I will write here so you will not get confused. This is, we are discussing intrinsic semiconductors. Intrinsic semiconductors. In intrinsic semiconductors, firstly we will consider the silicon. We will also study here the atomic structure of this intrinsic semiconductors. Firstly we will take silicon. Silicon has atomic number of 14, which has an electronic configuration of 284. Means in the outermost shell it has 4 electrons. So the valence shell has 4 electrons. So the atomic structure of silicon will look like this, in which the 4 outermost electron will form a covalent bond with another silicon atom. So its structure will look like this. There is also an important factor that silicon has an 1.5 into 10 to the power 10 number of electrons per centimeter cube volume. Means in 1 centimeter cube volume, silicon has 1.5 into 10 to the power 10 to the power 10 electrons, 10 number of electrons. Means this is a very large value in a small unit volume. So silicon has so we can say that silicon has a very large number of atoms in a small unit volume. That's the property of a silicon. Now we will consider another intrinsic semiconductor, that is germanium. As we see here that germanium has atomic number of 32, which will be electronic configured as 2, 8, 18 and 4. Means valence shell, which is the outermost shell, has 4 electrons in it. So we will call it as tetravalent. Tetravalent because it has 4 electrons in the outermost shell. Silicon also have 4 electrons in the outermost shell. So it is also called tetravalent. Next we will the factor which we have considered before, we can also consider it in germanium, that in germanium also there will be this will be 2.5 into 10 to the power 13, 2.5 into 10 to the power 13 per centimeter cube. Germanium has 2.5 into 10 to the power 13 number of atoms in a 1 centimeter cube volume. This is a very large value, and it is greatest value in all the three substances. Means in silicon, germanium, and in gallium arsenide, germanium has the highest number of atom per centimeter cube volume. That's the property, or that's the whole property of a germanium has a structure just similar like silicon because it also have 4 valence electrons. That's why I have not drawn the structure of germanium, because it is similar to that of silicon. Now we will consider the next intrinsic substance, which is gallium arsenide. In gallium arsenide is made up of two substances. Gallium arsenide is a compound which is made up of two elements. First is the gallium and second is the arsenic. Gallium has an atomic number of 31, which can be configured as 2, 8, 18 and 3. It has 3 electrons in its outermost shell, means in a valence shell. So it is called as trivalent. And arsenic has 33 atomic number, so it can be configured as 2, 8, 18 and 5. So 5 is the so in the outermost shell, which is the valence shell, has 5 electrons, so it is called as pentavalent. Its structure will look like this, in which the arsenic has 5 outermost electron, 1, 2, 3, 4 and 5. This must be shared by gallium atoms like this, and now the remaining gallium atoms, this and this, will again share by other arsenic atoms, and it will form a compound which will look like just similar like this. We can also find the energy gap at any temperature. Means as I have told you that on increasing temperature the properties of the material will also changing. So if you vary the temperature, the energy gap will also vary, and and we can find the energy gap at every temperature by this expression, which is energy gap at any temperature is equals to energy gap at 0 temperature minus beta naught T. This beta naught is a constant, whose value will be different for different materials. Here I have used the beta naught value for germanium, so I have found the result for germanium atom, and this and the germanium atom, as I have also made a tabular form of it, that by this table you can see that at 0 Kelvin, the value of energy gap of germanium is 0.785. at 0 Kelvin, the value of energy gap for germanium will be 0.785 electron volts, and the value of beta naught for it will be 2.4 into 10 ki power minus 4. So I have found the expression for 300 Kelvin temperature. So I have substituted the value of T as 300 Kelvin, and beta naught value I have substituted from here. So by solving this expression, you will get the value of 0.72 electron volt, which is the value of energy gap at 300 Kelvin temperature. So by this table, you can easily find out the value of energy gap at any temperature. You can note down this table. You should note down this table, and next we are considering another form. As you all can see that I have made another table. This is the mobility for different semiconductor materials. Mobility is nothing but a property to flow property to flow charge carrier freely. That's the mobility. Means mobility is nothing but a property to flow charge carrier freely in a substance. That's we called as a mobility. It is different for electron and different for holes. Its value is different for electrons and different for holes. So value of mobility for electrons and for holes for different materials, for different substances like germanium, silicon, and gallium arsenide will be different. So we can also define mobility unit simply by its formula, that is drift velocity upon electric field. As you all know that velocity is nothing but distance upon speed, so it is mass distance upon time. So it is so it will be distance by second, and electric field is volt per meter. By cancelling the terms, we will get sorry by we are not cancelling here. So simply this will goes in the numerator, and it will got multiply, and then the result will be formed like meter square upon volt second, which we also write as meter square volt inverse second inverse. You can note down this table. This is a very important table, and it should be asked in exams. There will be a numerical for which you have to find the energy gap for different temperatures. So you can use the value of mobility for electrons and holes from here. Here you can see that gallium arsenide has large number of mobility, because in gallium arsenide there will be less number of electrons in per unit volume. As we have discussed earlier, the number of atoms in per unit volume, there will be very less number of atom in per unit volume for gallium arsenide, so charge carrier will easily flow in that substance. So that's why the mobility of gallium arsenide is very high. This will be the final discussion for the intrinsic semiconductors.